Welcome back to the deep dive. Okay, today we have, I think, a really critical mission for you. We're going to extract the most vital, practical knowledge you need to actually run, secure, and automate a modern Linux system.
That's right. We're not really studying for a test here.
No, definitely not. The idea is to get the shortcut to being, truly well-informed about how these systems work day to day.
And that shortcut means looking at the kind of technical requirements you might find for something serious like the CompTIA Linux Plus certification. It covers a huge range from basic file stuff right up to complex automation.
Exactly. So forget the exam details, the 90 questions, 90 minutes, the passing score, whatever that is. We want the practical nuggets.
Yeah, the goal is to understand not just what commands or concepts exist, but why they're there and how they fit into this Linux ecosystem that's always evolving.
It really is a dynamic landscape, isn't it? Some things feel like they've been around forever.
Oh yeah, decades-old concepts, still solid.
But then you have other areas, especially like security, automation, scheduling. They're shifting fast towards these more integrated frameworks.
Understanding that mix the old and the new, that's really key.
Okay, let's dive in. Let's start right at the foundation. User identity and file system architecture. If you don't get this stuff right, well, everything else gets a lot harder.
Absolutely fundamental. And we can begin with file ownership. Seems simple, maybe, but it dictates who gets to touch a file right from the moment it's created.
Right, so we pulled a key point here about group affiliation. When I, as a user, create a new file, touch newfile.txt, which group does that file automatically belong to?
By default, it belongs to the user's primary group. Every user account has to have one main group assigned in, et cetera, password or wherever the user data is stored.
That's the one Linux grabs automatically.
Yep, that's the default.
So what does that actually mean in practice, let's say, for a developer working on a shared project? What are the implications?
Well, the implications are pretty big for initial access. If you and I are working on something together, but our primary groups are different, which they usually are,
Right.
then just relying on that default group ownership won't automatically give you, say, right access to my files, or vice versa.
Ah, okay, so it immediately makes you think about other methods.
Exactly. You either have to explicitly chi-sharp the file, change the group ownership, or more typically in shared setups, you manage permissions on the directory itself. You might set the SGID bit on the folder, for instance.
Override that default behavior for new files within that directory.
Precisely. So anything created in that directory inherits the directory's group, not the user's primary group.
Right.
Very common practice.
Okay, sticking with user setup, customization. The command line is where many of us live. I spend time setting up my aliases, maybe some shell functions, environment variables, but I want them to stick. Every time I open a new terminal tab, I want them there.
Yeah.
Where do those settings need to go? I admit I sometimes forget which dot file is the right one.
Yeah, that's a common point of confusion. For settings that should load for every new interactive shell, you put them in the specific shell's RC file. That stands for run commands.
Ah, the RC file. Okay.
It's the configuration file that gets sourced every time you fire up a new interactive shell session.
So for good old bash, that's .bash RC in my home directory.
Correct.
And if I'm using Z shell or zsh, then it's .zsrc.
Yep, .zsrcfa. That's the place to personalize your interactive environment, make sure your shortcuts and settings are always ready to go.
Because if you put it somewhere else, like maybe a .profile or .bash profile.
Right, those typically only run for a login shell, like when you first SSH in or log in on the console, not usually for every new terminal window or tab you open afterwards. So the RC file ensures that persistence for new interactive sessions.
Got it. Okay, let's shift gears slightly to file organization, links. We absolutely need to nail the difference between a hard link and a soft link, which is also called a symbolic link or symlink.
Yes, this trips people up all the time, but understanding the distinction is, well, it's critical for managing files properly and ensuring data doesn't just disappear on you.
A soft link, the symbolic link, feels kind of intuitive, right? It's like a shortcut on your desktop. It just points somewhere else.
Exactly. It's a pointer to a path name.
But a hard link, why would I use one? Knowing the big limitation is that they generally have to stay on the same file system, the same disk volume. That sounds like a pretty major drawback compared to a soft link, which can cross file system boundaries.
That's a great question. The limitation is real, but the strength of a hard link lies in its fundamental connection to the actual file data. A hard link isn't just a pointer, it's effectively a second name or directory entry pointing to the very same inode.
The inode being the data structure on disk that holds the file's metadata and points to the data blocks.
Precisely. So because a hard link points directly to the inode, it acts as a reference counter. Meaning the file data itself, the actual bytes on disk, only gets deleted when the last hard link pointing to that inode is removed. So if you create a file, it has one link. You create a hard link to it, and now the inode's link count is 2. If you delete the original file name...
The data is still safe because the hard link still exists. The count is still 1.
Exactly. The data only vanishes when that link count hits 0. It guarantees data survival as long as at least one hard link exists.
Ah, okay, so the hard link is like an anchor for the data itself. Whereas the soft link is just a signpost. If the destination it points to gets deleted.
Poof, the soft link becomes a broken link. It points to nothing, throws an error if you try to use it. That resilience, that data safety net, is why hard links, despite the single file system limitation, are still a fundamental part of Unix and Linux file systems.
That clarifies the utility perfectly. Okay, let's pivot now. Moving into automation, scheduling, and logging. This is really the heartbeat of keeping servers running smoothly, especially at scale.
Yeah, managing tasks over time and keeping track of what happened. Essential stuff.
For, decades, scheduling automated tasks meant one thing, cron. Writing cron tab entries.
The classic. Yep.
But modern Linux distributions, especially those built around systemed, have introduced a different way. What's the modern system unit that essentially replaces or enhances the role of a traditional cron job?
In the systemed world, that function is handled by a timer unit.
A timer file.
A timer unit. Okay, but why the change? What was wrong with cron? What does a system timer do better?
Well, a couple of key things, really. Primarily, integration and logging. Cron jobs kind of ran in their own little world, separate from the main system service manager.
Right. You'd pipe output to devnull or maybe a log file, but it wasn't neatly tied into system logs.
Exactly. System timer units, though, they run within the systemed ecosystem. This means you get much better control. You can set up dependencies, don't run this job until this service is up, things like that. And crucially, their output and execution status are automatically captured by systems' centralized logging.
Ah, okay. And that centralized logging system is the journaled service, correct? That's the one. Journaled.
So why is that approach considered superior to the old way of just having tons of different text log files scattered in varlog?
The big advantage of journal is that it collects logs from everything the kernel, system services started by systemed, applications, syslog, and stores it all in a structured, indexed, binary format. Centralized.
Structured and binary, meaning it's not just plain text.
Right. It includes metadata automatically, which service generated the message, the timestamp, the severity level, the process ID, all indexed.
So the practical benefit is,
Yeah.
instead of me having to grep through maybe 10 or 20 different log files in varlog trying to piece together what happened.
You use one command, .journal_table, and you can filter instantly. Show me all logs from the Schursted service in the last hour. Show me only critical errors across the whole system. Show me logs related to a specific process ID. It makes troubleshooting vastly faster and gives you way more context than digging through isolated text files.
That makes a huge difference when you're under pressure trying to fix something. Okay, let's connect this to managing lots of systems. If I'm using a configuration management tool, Ansible is a really popular one. How does Ansible know which servers it's supposed to configure or run commands on?
Ah, that's defined in the inventory file. This is probably the most fundamental piece of any configuration management setup, whether it's Ansible, Chef, Puppet, Salt. You need an inventory.
So the inventory is basically the address book.
Pretty much, yeah. It's a file, could be INI format, YAML, even a dynamic script that pulls from a cloud provider that lists all the servers, the hosts that the tool should manage.
And you can group them too, right? Like web servers, database servers.
Absolutely. Grouping is essential. It lets you target your configurations, your playbooks in Ansible terms to specific sets of machines. Run this set of tasks only on the web servers. Run that database setup only on the DB group.
So if my Ansible run fails because it can't even connect to the servers I intended, chances are the problem isn't my playbook logic, it's my inventory file being wrong.
That's often the first place to look, yes. If the inventory doesn't correctly list the hosts or define how to connect to them, IP addresses, SSH keys, etc., then nothing else matters. Your automation engine doesn't know where to go.
Got it. Foundational. Okay, let's move to our final section now, focusing on security and modern development workflow.
Two really important areas that have seen a lot of change.
Definitely. So standard Linux file permissions,
Yes.
owner, group, other, read, write, execute, that's discretionary access control, or DAC, been around forever.
The bedrock.
But in today's world, with sophisticated attacks, just relying on users to set permissions correctly, well, it's often not enough. What security mechanisms are built into Linux to provide much more fine-grained, system-wide security policies that go beyond basic DS?
Okay, so this is where you get into things like Linux Security Enhanced Linux or a Parmer. These are the big players providing mandatory access control, or MS.
Mandatory access control, MS versus DAC. That distinction feels really important. Can you break down how MS elevates security compared to just standard user permissions?
Sure. With DA, it's discretionary. If you own a file, you decide who gets access. You can chmod 777 it if you want, making it wide open.
Even if that's a terrible idea from a security perspective.
Exactly. Felon takes that discretion away. Instead, the system administrator defines the central security policy, and the kernel itself enforces it. It's mandatory. Users, even the root user sometimes, cannot override these core policy rules.
So give me an example. How would MMAT help with, say, a compromised web server process?
Okay, classic example. Under DSC, if your web server process, like Apache or Nginx, gets compromised, and maybe it's running as the www data user, it can potentially access anything that the www data user has standard file permissions for. If it somehow escalates to root, game over.
Right.
Under a Mac system like Linux, there would be a specific policy written for the web server process. This policy might state, the HTTPD process is allowed to read files only in varshu, write logs only to varlet TPD, and bind only to network ports 80 and 443. It is explicitly denied access to, say, etc. shadow or user home directories, regardless of file permissions.
Wow. So even if that process gets compromised, or even gains root privileges somehow, the kernel's MIC policy still severely restricts what it can actually do. It's contained.
Precisely. It creates these security contexts, these labels on processes and files, and the policy defines allowed interactions between them. It enforces the principle of least privilege at a much deeper kernel-enforced level. It's a powerful defense against exploits and misconfigurations.
Okay, that makes sense. Shifting to the developer or sysadmin writing scripts. Let's say I'm automating tasks using Python. I constantly hear people say, you must use a virtual environment. Why? What's the big deal about creating this extra directory structure and activating it? It seems like extra steps.
It might seem like extra steps at first, but the primary benefit is huge. Dependency isolation.
Well, dependency isolation, you mean preventing dependency hell.
That's exactly it. You know the situation. Project A needs version 1.2 of some library, but Project B needs version 2.0 of the same library. If you install them both globally on the system,
something's going to break. Or worse, maybe the operating system itself relied on version 1.0 of that library for some critical function, and you just broke your OS.
Bingo. A virtual environment creates a self-contained little bubble for your Python project. Inside that bubble, you can install the exact versions of the libraries your specific script needs using pip without affecting any other projects or the main system Python installation.
So Project A gets its own environment with library v1.2, Project B gets its own environment with library v2.0, and the system Python stays clean.
Exactly. It keeps everything tidy, prevents conflicts, makes your automation reliable, and stops you from accidentally wrecking the underlying system. It's absolutely standard practice and honestly essential for any non-trivial Python work these days.
Okay, good advice. Let's talk version control now, specifically Git. We've all hit this scenario. You're deep in coding a big new feature.
Yeah.
Your working directory is, let's just say, a mess. Files modified, some staged, some not.
Yeah.
Suddenly, a critical production bug report comes in. P1, drop everything.
Yeah. Gotta switch branches now and fix it.
But I can't commit this half-baked, probably broken feature code. It would pollute the history, and it's not ready. So what Git feature lets me just save my messy state temporarily, get my working directory clean so I can switch branches without making an actual commit?
The lifesaver you're looking for there is git stash.
The stash.
Right. You run git stash, and Git takes all your tracked modified files, both staged and unstaged changes, and basically tucks them away safely onto a stack of temporary changes. It then reverts your working directory back to the state of the last commit, the head.
So instantly clean, ready to switch branches.
Instantly clean. You switch branches, make your urgent bug fix, commit it properly, maybe push it, then you switch back to your original feature branch.
And then, How do I get my messy work back?
You run git stash pop.
Hmm.
Git takes that most recently stashed set of changes and reapplies them to your working directory, trying to merge them back in. Your mess is restored exactly as you left it, ready for you to continue working.
It's like a perfect little temporary locker for unfinished work, essential for context switching.
Absolutely essential for fluid development workflow.
Okay, finally, let's touch on one more command line evolution. For years, maybe decades, the command we used to check network interface configurations, IP addresses, MSE addresses, was ifconfig.
The old standby.
But in most modern Linux systems, while ifconfig might still be available sometimes, it's largely considered deprecated. What's the modern, more powerful tool that has replaced it?
That replacement is the IP utility, part of the iproute2 package.
The ipt command. And it's more than just a simple replacement, isn't it? It does a lot more than ifconfig ever did.
Oh, definitely. The IP utility is much more versatile. It handles not just displaying and configuring interfaces and IP addresses, EP add, uper-outlink, but also managing routing tables, iproute, neighbor discovery ARP cache, ipna, network tunnels, and more, all under this one consistent command structure.
So where you used to need maybe ifconfig plus route plus ARP and maybe other tools,
Now, the if command often consolidates that functionality. It's designed to be more scriptable, more consistent, and provides more detailed information. It really is the modern standard for low-level network configuration and inspection on Linux. A perfect example of how tools evolve to become more powerful and unified.
So that brings us to the final thought for you, our listener. We've seen these foundational concepts that are relatively stable alongside these advanced frameworks for automation and security that are arguably becoming more critical but are also complex and always changing.
It's a real tension.
It is. So the question to mull over is this. As someone learning or working within the Linux ecosystem today, how should you prioritize your limited time and energy? Should you focus first on achieving absolute deep mastery of those bedrock basics, the things that don't change much? Or should you perhaps dive headfirst into understanding and mastering the rapidly evolving, complex, but increasingly essential advanced frameworks that really define modern system architecture and operation? Where's the right balance for you?
That's a tough prioritization call, something to think about.
Indeed, plenty to consider until our next deep dive.